Now let's get into some actual radio things. Hi guys, I'm Whitney Knitter with Knittronics and welcome back to another video. Before I get into it, of course, covering all the stuff off the top, all thoughts and ideas presented in this video are my own and do not represent the thoughts and opinions of any company I am currently or have previously been associated with. Furthermore, this video is another partnership with Digilent. I'm very lucky to be working with them again. They did send me the hardware I'm about to show you and have sponsored this video. So, with all the housekeeping stuff out of the way, let's get into it. Every time I set the Eclipse Z7 aside after a project, it seems to find a way to spawn itself back into the middle of my desk with some cool new feature based upon either new software or hardware. Last year, Digilent released a special embedded Linux image for the Eclipse Z7 that made it compatible with their test equipment software waveforms. So you could essentially turn the Eclipse Z7 with some combination of their Zmod peripheral boards into a USB oscilloscope, just like anything from their Analog Discovery or Analog Discovery Pro series. On top of the inherent functionality that comes with the Eclipse Z7 from the sense that it is an FPGA development platform, that extra software out of the box gives it a whole new purpose, whole separate purpose as a piece of test equipment straight out of the box. For those not familiar, the Eclipse Z7 is an FPGA development platform, like I mentioned, based on AMD's Zinc 7000 series of system-on-chip FPGAs, in addition to peripherals such as USB, Ethernet, PMOD. The Eclipse Z7 boasts two of Digilent's Zmod interfaces. Zmod is based upon the Syzygy standard interface, which is basically it's an option for high-speed I/O in a compact footprint, something a little bit smaller than, say, FMC. So, like I mentioned, by utilizing different combinations of the Zmod peripheral boards and different supporting software, the Eclipse Z7 can take on completely different development platform capabilities. Earlier this month, Digilent launched the new SDR Zmod peripheral board and an accompaniment and special Alpine Linux embedded image for the Eclipse Z7. This included drivers that are compatible with common SDR platform software such as GNU Radio, SDR Sharp, and HD SDR. Now, I do want to point out that as of this time, or as of the time of filming, all of the current Zmod peripheral boards that Digilent has available is some form of ADC or DAC chip. So analog to digital conversion or digital to analog conversion. And the main difference is either different chips to enable different sample rates, or some of the bigger differences, especially the differentiators between the SDR Zmod and then the digitizer Zmod that was released late last year, is going to be the analog circuitry surrounding the analog to digital converter chip. Looking at the SDR Zmod specifically, even though it has the same chip, the AD9648, put up on screen if I got that wrong, even though that's the same chip as the digitizer Zmod, the surrounding circuitry on the SDR Zmod is what gears it more towards SDR applications. The first of which is the input impedance for the analog side of things is the 50 ohm input impedance compared to the 1 mega ohm previously on there. 1 mega ohm, that's a typical input impedance for something like an oscilloscope application, but 50 ohms is more common or the standard for radio applications because that's typically what you try to match your antennas to. Furthermore, the output is AC coupled on the SDR Zmod compared to DC coupled on the RF digitizer. This is because any of the waveforms that are coming out of the ADC on an SDR are going to be at the passband level, not at the baseband, so you want to block any of those DC components in the signal. And the final thing is that the SDR Zmod does not have the low-pass filter on its output like the digitizer Zmod does. The digitizer Zmod has a low-pass filter on its output that caps off at 60 megahertz. However, the SDR Zmod does not have that, so you can play around with undersampling to have a broader bandwidth for your channels up to about 470 megahertz. However, as some of you might be catching on at this point, the SDR Zmod only has an analog to digital converter. Therefore, it can only be the receive part of your chain in your radio application, which is why the supporting software also has drivers for the AWG Zmod, or the analog waveform generator Zmod. This is the same peripheral that I used in my last video to generate different waveforms to run my test applications. So it is this combination of the Eclipse Z7 with Alpine image, the SDR Zmod, and the AWG Zmod that gives you the full transmit and receive chain in your SDR development platform. And therefore, this SDR Zmod bundle, I believe, is what it's being dubbed by Digilent. I could be wrong. Again, I'll put an asterisk on the screen if I'm wrong. Favorite thing to do. But that is the new functionality that my Eclipse Z7 has spawned itself back into the middle of my desk with. So what the Alpine Linux image is doing on the Eclipse Z7 is you'll notice that we have the Ethernet connected. There is a TCP/IP server running on the ARM core of the Zinc chip. That's sitting there listening to a TCP/IP port, waiting for commands for settings such as what to set the center frequency to for the actual passband RF output, what the sampling rates are throughout the chain, or the RF chain, which channel of the Zmods to use respectively. So there's two channels on both the AWG Zmod and the SDR Zmod. Then coming out of the ARM core, there is a bit stream in the programmable logic of the Zinc that has all of your stuff like your digital up and down conversion, your IQ modulation, and then it's also taking the samples back from the SDR Zmod and streaming those back to GNU Radio. I'm personally using GNU Radio because I'm using Linux. SDR Sharp and HD SDR, I've only seen Windows variants, but there are full setup instructions for those on Digilent's website. I'm gonna go over the GNU Radio setup here. So in addition to the actual embedded Linux image running on the Eclipse Z7, there is also a repo for the SDR Zmod that contains drivers such as the out-of-tree blocks for GNU Radio, so the Eclipse Z7 source and sync blocks. It's pretty easy to get going with that. You just take the repo, clone it, change directories into the desired project. So in this case, we're looking at the SDR transceiver, so we can look at both transmit and receive. Set the current directory as the GRC blocks path. You could also be outside of this directory if you want, and just make sure wherever those out-of-tree blocks for the Eclipse Z7 source and sync are, just make sure you pass that as the GRC block path to your environment. And then launch GNU Radio. The repo does also include an example FM receiver project. It's just the bare bones basic FM radio receiver project. So that's obviously where I started, just to make sure my SDR Zmod hardware itself was alive. So that's why I have my dipole antenna set up here. I'm gonna try to listen to some of my local radio stations. So I have it set to about 100 megahertz. That's kind of where all my local ones are, about 99 to 100. I explained in another previous blog post about how you choose your quarter wavelength of your dipole antenna, because these are retractable and I can change the length of them. But about 30 inches equates to the quarter wavelength of like a 99 megahertz center frequency target. And I do have that set up. I kind of have all the demos set up at once so I don't have to change it. So I have my antenna on port 2 of the SDR Zmod right now. So I'm going to come into the FM receiver and I'm going to change. So I know because there is a TCP/IP server running on the Alpine Linux image that the term port is a little bit overloaded here and might seem confusing. But the port that you see in the Eclipse Z7 source and sync blocks actually refers to the 2 channels on either the AWG Zmod or the SDR Zmod. So port 1001 is channel 1 and port 1002 is channel 2. Right now I have mine set to 1001 because that's what I originally tested. So let's change that to 1002 and generate our block here. I also need to, I need to change my sound output so you can hear it. So I have about center frequency, I think the one I was going for, let's do 99.7. I think that's just like the local news station here. And, oh, I forgot the main part. Oh, and I just closed the, you know, if I want to demo something, it does help to turn on the board. I wonder how many of you are screaming at me. Can you tell I film these kind of late at night after my normal workday? Because it's just, I'm fried clearly. So let's, there we go, that helps. Like I mentioned, because there is a server application running on the Eclipse Z7 that is waiting to communicate with GNU Radio, we also need to start that server application on the Eclipse Z7. So not only did I forget to turn the board on, I forgot to start the server application. So GNU Radio can't talk, doesn't have anything to talk to. So the default login for the Linux image for the Eclipse Z7 is root, and the default password is change.me. And then it gives you instructions for changing it, obviously. You're gonna wanna do that. So once you boot up the Eclipse Z7, you wanna figure out what the local IP address it's been assigned to, because this Ethernet connector is actually connected to my router. There is a way to set it up with internet sharing directly to your computer. I haven't gotten that to work. So I know it's local IP. I've got that set in GNU Radio. So I'm going to change directories into apps, and then the same application name that I'm trying to run on GNU Radio. So there's the corresponding SDR transceiver application on the Eclipse itself. The file layout's the exact same as in the repo on the host computer. And then I'm simply going to run the start script. And there we go. Helps to turn things on. Like I explained, our first test is we're gonna look at channel 2 of our SDR Zmod to listen to some local radio stations. I don't have a ton of DSP in here, so it's not gonna sound the clearest. We wanna make sure there's something. Okay, so a little bit of sound difficulty. Let's try that again. It's really tough getting all of these different things to record audio the way I want. So, and there we go. So at this point we know we are getting, at least, albeit noise, we are getting throughput from our antenna through the SDR Zmod to our FM receiver. So even though I can't remember where my local radio stations were, I had this figured out the other day, we're at least proving we're getting something through our antenna, through the SDR Zmod, and back to GNU Radio. The next thing I want to do is make sure I have the transmit part of my chain working. So let me switch over to that setup and show you what I have. I found it, 99.7. You can kind of hear it, it's really quiet. Like I said, there's no other filtering I have on here. It's just basic, like dumping straight into the audio sync. I don't know if it'll come through on the mic, but it's like, you can kind of hear like the garbled song underneath everything. Okay, just wanted to prove that. Let's move on to testing the transmit side. So my favorite thing to do, or well, my favorite's kind of an odd word. What I like to do with a transmitter of any sort before I try to output actual data from it, actual modulated signal, I want to make sure it can output just a continuous wave or CW tone, which is just a single unmodulated frequency. So to accomplish that, I created a really simple little flow graph, a new one, and all I have is a constant feeding straight into the Eclipse Z7 sync at the desired center frequency I want. And then I have that configured to output a single tone on channel 2 of the AWG Zmod, and then I have that going back into, I busted out my ADP 2230 again to make sure that I see that CW tone on the spectrum analyzer from the 2230. So I have this set to a center frequency of 10 megahertz because I do need to stay within the constraints of my 2230 because this can output a higher frequency than that can measure, but so I'm gonna actually I can go up to 20 megahertz at least on the 2230, so I'm gonna change the center frequency on this guy to output 20. I've got my spectrum analyzer here. I'm gonna go ahead and run. So it's running from GNU Radio, and there you go. Now you see our 20 megahertz CW tone from the AWG Zmod. So we're alive, the proof of life. Woohoo! All right, now let's get into some actual radio things. Last month, I had created a little audio transceiver loopback flow graph for my B205 Mini. So taking in my audio from my mic, well, my AirPods or my computer, putting it through the FM transmit modulation block that GNU Radio has, outputting it, and then doing the same receive demodulation on the other side and seeing if I could hear myself talking coming out of my speakers. We got that working on the B205 Mini, so I thought it would be good to do that on the Eclipse Z7 SDR Zmod bundle as well, because since this is a new setup, there's a new IQ modulator, we're gonna have to play with the sample rates and DSP and that entire chain. So let's take a look at that. So on the Eclipse Z7 source, there's some, based upon how all of the math works out in the HDL logic for the IQ complex number representation, there are fixed sample rates that the SDR Zmod transceiver is capable of. There's a 1.536 megahertz, and then it goes down in different multiples. Ultimately, there are multiples of 48 kilohertz, which is nice because we're doing audio. So all of my audio coming out of my speakers and being sampled by my microphone, that's all 48 kilohertz. So to start with, I like oversampling. Typically, my opinion is let's sample as much as possible, get all the data, and we can always filter down and decimate from there. So to start with, I've chosen the max sample rate that the SDR Zmod is capable of, which is 1.536 megahertz. I'm taking that down with a rational resampler, decimating that by 2 to get that down to my quadrature rate, which I have set at 768 kilohertz right now, and then further decimating that down to the 48 kilohertz to ultimately go into the audio sync. And then I just repeat that same process backwards of starting out the 48 kilohertz, interpolating up to kind of in the mid-range of getting my audio rate up to 192 kilohertz before translating it on the quadrature rate or sample rate there of 768, and then ultimately interpolating it up to that 1.536 megahertz that we're throwing out into the Eclipse Z7 sync, which is outputting on the AWG Zmod. So let's take a look at how that works. And I'm talking, and you can tell there's something, and it's just static. And it's not great. What happened? So in my overabundance of data mindset, because I'm oversampling, I have lots and lots of data that I am asking both the Eclipse Z7 to process and GNU Radio on my host PC to process. And it's too much to keep up. I'm getting lots of underruns. You can see by the AU output, there's simply, I've got too much data there, and even trying to decimate it down, it simply can't happen fast enough to keep up in real time. Therefore, I'm just getting garbly gook output. So I have been proven wrong. My abundance sampling mindset was wrong here. So let's scale things down and start at a more appropriate passband frequency. So I scaled things back. Less is better. Let's take the sampling rate down to just what we need. So I pulled back, even though my center frequency is still the same, I'm still transmitting and receiving at 100 megahertz. I have pulled back the sample rate at the initial source and sink of the SDR and AWG to 384 kilohertz. That way I'm only decimating by a total of 2 and 4 to get down to my 48 kilohertz, and then on the way out I'm only interpolating by a total of 4. So less data to overflow everything with. Let's see how this sounds, hopefully. So, can you hear me now? Haha! Okay, I'm not gonna lie, I get kind of distracted with this. And I just sit down here and talk to myself. Not that I wasn't already a crazy introvert, but there you go. So a mini lesson in DSP. I do have all of this. Okay, I'm probably annoying. Let me turn this off. I do have all of this explained in much more eloquent detail in writing. That's gonna be in a blog post linked here that is an accompaniment to all of these demos. And like I said, getting in the actual math of the complex numbers and handling the IQ and all of that turns into a whole lecture itself. But definitely check out the written post that goes with this video to kind of understand that better. So I feel like that shows a pretty good demo of everything up and working. We made sure all the channels were alive on both the AWG and the SDR Zmods. Everything can talk. We got great audio output after wheeling back my oversampling mindset. No regrets, live and you learn. But the last thing I wanted to go over in this video, because I think it's kind of a slick thing, is a little bit more in depth in the repo that is available for the SDR transceiver applications. So I had cloned the project here. So Eclipse Z7 notes is the repo. And what's really awesome is there is a make file in here along with all the source files to rebuild the SD card image for the Alpine Linux image from source, and then also rebuild a bit stream from source. So when you run the make file, in particular the bit stream, it creates this temp folder in here with the actual Vivado project of what's going on in the programmable logic of the Zinc chip. That's actually what I did to take a look through to figure out what was going on in everything. Because the Eclipse Z7 is not the only board from Digilent and just in general that offers that Zmod connector or syzygy connector. So I think this source project, you could, I mean, it would take some, I wouldn't call it easy, but there is a straightforward path to take this source project and change the constraints file, target it towards a different FPGA with a different chip on it. I think that's kind of an exciting little tidbit of look through here. And then also I think it's a great exercise to, you can look on there is a great block diagram on the engineer's website that actually created this whole Alpine Linux image. That's a block diagram of all the DSP that's happening in the bitstream here. I'll pop that up over here. But you can take that block diagram, what's going on, compare it to how he's implemented it in the actual Vivado project here, and see kind of that transition from DSP theory to how you implement it in an embedded system. So things like your complex multiplication, doing your floating point conversion, all of that stuff. I know a lot of people are probably like me, where seeing an example is the fastest / most effective way that I learn. So I just wanted to point that out as a little Easter egg to follow through and potentially expand on this entire setup with. That wraps everything up for this video and my demo. Before I go, just a quick reminder, we're a fan of shutting down safely. So returning back to the terminal here, this particular image of Alpine uses the halt command instead of shutdown. So we're just going to halt, wait till we get the power down confirmation, requesting to reboot, system halted, woohoo! Now we can loop. So while the Eclipse Z7 SDR bundle isn't quite as compact as the B205 Mini or my RTL SDR dongle, the reconfigurability it gives me, I'm very excited about, since I could simply change out the SD card between the Alpine Linux image and the Waveforms Linux image. I can swap out Zmod interface boards to make it a 4-channel transmit system or a 4-channel receive system. Obviously, I'd have to change some of the support software, but either way, being able to change things out, that's very exciting. So suffice it to say, I'm a big fan so far. Thank you again to Digilent. I love all of your stuff. It's fun to play with. And I still don't know how to say bye, so bye. Okay, I'm gonna stop talking.